In this lesson, we're going to be talking about the trapezoidal method for approximating definite intervals. As you can see here with the picture I have illustrating what the trapezoidal method would look like. It's sort of similar to what we've done with our Riemann sums, but now we're going to be using trapezoids to find the area under the curve rather than rectangles. Just as a quick review, let's take just a second and go back and look at our left point Riemann sums, our right point Riemann sums, and our midpoint Riemann sums. Kind of remember what those would look like. Remember that as we were doing these, if we did the left point Riemann sum, what was going to happen was we were going to pick 2 points in this first case, if you'll see. It went from 5 to 10. And since 5 is farther to the left than 10, then we use the height at that value to determine the height of each one of our rectangles. And you'll notice that each one of these, they always use the point over on the left to figure out what the height's going to be for the rectangle. One there too. All right, then on a right point Riemann sum, we do it exactly the opposite. We look at our first 2 values that we're going to be calculating for our width of our rectangle, which in this case would be between 0 and 1. 1 is farther to the right, and so we use the height there at 1 to draw our rectangles. And then between 1 and 2, we use the height at 2 and draw our rectangles, and so on, and approximate those. And we talked about that. In some cases, the left point might be an over approximation. Depending on the curve, it can actually be an under approximation. Same thing was true with the right point. In this case, the example we've got shown here, you can tell that our approximation is going to be an under approximation, although I could also draw one where the right point approximation would be an over approximation. And then we talked about the midpoint Riemann sum, and what you do in that case is if my first interval is from 1 to 2, we go to a half and then use the height at a half. Oh, sorry, the first one's from 1 to 1.5. Didn't look at my scale there very well. So they use 1.25 and use the height at 1.25 as my height of the first rectangle. The second rectangle went from 1.5 to 2, and they used the height at 1.75 to get my height of this next rectangle, and then so on. We go from 2 to 2.5, so they use the height at 2.25 to get the rectangle's height there. Okay. Then we also discussed the fact that if you're only going to do one of the 3 of these, then your midpoint Riemann sum would probably be the better one to do. Now remember that Riemann said that if we do enough of these, both left point, or all 3 of left point, right point, midpoint, they'll eventually give you all the same answer. That's not going to be obvious here because you don't have very many rectangles drawn in here, but imagine if we broke this up into thousands of rectangles, then what's going to happen is the 3 values will end up becoming the same. Now what we're going to do now is look at the trapezoidal method and what we do with it. How do we come up with a formula for that? Let's just first of all look at a little example, kind of applet of what's going on with the trapezoidal method. Here's an example of a trapezoidal method. Your curve is the square root of x cosine of x plus 4. And right now, it's set to have only 3 trapezoids. Now, in this example, let me move this out of our way. We can actually change the number of trapezoids that we're going to have. And notice what happens to the area as I do that. Also look at the way the picture's drawn. We went from, it looks like 1 to 10, and with 3 trapezoids. So notice that in that case, if I went from 1 to 10, then that would be 9 units with 3 trapezoids. That would make them a total of 3 units separated apart. So the first one goes 1 to 4, that's 3 apart. 4 to 7, that's 3, and then 7 to 10. So there would be my lines for my trapezoid, and then what I do is I connect the heights at each of those points to make my trapezoid. Okay. Now you can see in this case, in the first trapezoid we're over, in the second trapezoid we're under, and in the third trapezoid we're over. So this would probably end up being an over approximation as a final approximation. So let's throw in a few more trapezoids. There's what's going to happen if I have 4. You can see that we're now starting to get a lot closer to what the actual area looks like. Let's go through some more. If we get up to around 10, that's a fairly decent approximation. And you can notice that as I keep increasing the number of trapezoids, that now what's happening is my curve is being approximated very well by that shape because the trapezoids are covering more of the area under the curve, and they're also going over the curve by less every time. So we're up to, let's say, 25 trapezoids, and we have a fairly good approximation. And if you look, it appears that our area is probably going to be somewhere around 33. Because as I do more trapezoids, notice that it went closer to 32 or 33. And now we're actually dropping a little bit below 33. So it probably is a little under 33. It should be fairly close to 33. Okay. So that's the idea behind what the trapezoidal method looks like. So let's see if we can break this down now and come up with a formula to maybe be able to go through trapezoidal method. So here's a picture. I don't really know what the curve is. It doesn't really matter in this case. I'm just going to try to set up the formula anyway. So here's my graph, and I've kind of gone ahead and I've got some trapezoids drawn in underneath here. Here's what I'm going to do. We don't know where this starts or ends. Let's just say it's from A to B. So we start at A, we end over here at B, and we've got N subintervals, like we talked about with our Riemann sum. Then what we can do is talk about how wide each one of those subintervals would be. Well, if you think about that, if you've got to go from A to B, the distance between those would be B minus A. But then I'm going to divide that up into n parts. So a lot of times when you look at this in textbooks, you'll see that called delta x, which in this case would be each one of these divisions here. Now, these are evenly spaced out. They're designed to be that way mainly because it's just easier to keep them the same amount. Although we will look at an example here in a minute where they don't have to be evenly spaced out. So that's my delta x. Well, each one of my x values has a corresponding y value, and they just started counting at x sub 0, and that's just pretty standard for this notation. You didn't have to. You could have started at x1, x2, x3, but they started x0, x1, x2. So what we're going to do then is assign a corresponding y to these. y0, y1, y2, y3, y4, y5, and y6. Now in a minute we're going to assume that, let's say this kept going on, or we had more rectangles, or trapezoids you should say, in here than just what I've got drawn now, the 6 that I have drawn now. Alright, so the formula for the area of one trapezoid, let me move this up so we can get this on here. The area of a trapezoid is 1/2 the height times the sum of the two bases, B1 plus B2. Now the important thing in a trapezoid you remember is that the bases connect are the two parallel sides, so they have to be parallel. Very good parallel symbol there. Okay, they have to be parallel, and then the height is the distance between the parallel sides, so that's h. If I look at my picture, my trapezoids are kind of drawn upside down, or up on their side. Each one of my trapezoids is looking something like this, where here is going to be some y value. Let's say that first one is y0 and there's y1. And then this distance here between them is my base, or my height, not my base, my height. So these are my two bases, y0 and y1, and then my height is h, which in our picture we call delta x. So now, for the first trapezoid, here's how the area is going to go. It's going to be 1/2 the height, which is delta x, times the sum of the two bases. But the bases of the first trapezoid are y0 and y1. Then I'm going to add to that the next trapezoid, which would be 1/2 delta x. Now my bases for the second trapezoid, which is this one here, would be y1 and y2. Now we'll add on the third trapezoid. The third one's here. So it's going to be 1/2 delta x, and it's going to have bases of y2 and y3. And then we'll go to the next trapezoid, which would be y4, or would be the fourth trapezoid, sorry. That would be 1/2 delta x. And in the fourth trapezoid, my bases are y3 and y4. Now, we would keep doing that, and I'm going to pretend we would divide this up now into more sections than what I've got drawn here. Because right now, again, I'm pretending we only have 6 trapezoids. But if you wanted a really accurate approximation for this, you'd do a lot of them. So let's, instead of calling this y6, let's call it y sub n. Meaning it's the nth trapezoid. So if we had 10 trapezoids, that'd be y10. Or 20 trapezoids, that'd be y sub 20. So then the last trapezoid that I'd add on the end, this is where the notation gets a little tricky, would be 1/2 delta x times, well, my last base is yn, or y sub n, and the base right before that would be y sub n minus 1. So if this was y sub 10, this would be y sub 9, 10 minus 1. Then before that, the trapezoid previously before that would be would be 1/2 delta x. And then the last one would be y sub n minus 1, plus the one previous to that would be y sub n minus 2. Okay. So if this is y sub n, right before it would be y sub n minus 1. Right before y sub n minus 1 is y sub n minus 2, and then we could keep doing backwards. All right, so let's see if we can start looking at what we have here. So we've got, let's treat this now as one big term. Then this is all one term because there's a plus between those. So now we've separated terms. Here's another one, then a plus. Here's another one. Here's another one. Here's another one. Okay? Well, if you look at that, you'll notice that all of those have something in common. They all have a 1/2 and a delta x. So what I'm going to do is I'm going to factor that out. So I take out a 1/2, a delta x from everything, and when I do, so that's gone from each one of them. I want to look at what's left over. Well, what I've got left over in the first term is y sub 0 plus y sub 1. Plus, from here. Then the second term I have left over, y sub 1 and y sub 2. Then plus, from here. But in the third trapezoid, I have left over y2 and y3. Plus, the next one would have y3 and y4. Plus, now we're out here, y sub n minus 2 plus y sub n minus 1 plus, and then the last trapezoid would be y sub n minus 1 plus y sub n. But now if I look inside of all that big set of parentheses, I have some common terms. Here's a y sub 1 and a y sub 1, so I could combine those and make this y sub 0 plus 2 y sub 1. Plus 2 y sub 2, there's 2 y2s, plus 2 y sub 3s, plus 2 y sub 4s, plus, now remember there's actually supposed to be a dot, dot, dot right there. I'm going to skip out to the end. We've got a y sub n. There's only one of those, but there's 2 y sub n minus 1s. Now, if you think of this in terms of the picture, that's going to make sense. Notice what happened. All the bases, except for the very first one, y sub 0, and the very last one, y sub n, are actually getting doubled. Now, look at that in terms of your picture, and that should make sense. Let's try to erase some of the stuff we've got in here. So here was y0, y1, y2, y3. We'll just go out. We'll make that n minus 1. Some dot dot dots there. Y sub n. Okay, here's what's going to happen. This side of the trapezoid, that height, or in this case base 1, is only used in one trapezoid, the very first one. But then this segment is used twice. It's the bottom of trapezoid 1, and it's the top of trapezoid 2. So that's why you're seeing it get used twice, because it's going to be used in two different trapezoids. There was trapezoid 1, there was trapezoid 2. Then the next side, same thing. Y2 is the bottom of trapezoid 2, but it's the top of trapezoid 3. Y3, bottom of trapezoid 3, top of trapezoid 4. Then we skip all the way out to the end. Y sub n is only used once because it's just the bottom of the last trapezoid. It was only used once in the trapezoids, but y sub n minus 1 would have been used twice. It was an inside base. So it would have been the top of the last trapezoid and the bottom of the next to the last trapezoid. So here is your formula for trapezoidal method. You'll need to memorize that formula. Some books write it a little differently. Instead of using delta x, they'll put an h there for the height. Okay? So you might actually see it, and let me go ahead and extend it one more time here for you, as 1/2 the height, then y0 plus 2y1 plus 2y2 plus 2y3 plus dot 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 y sub n. Now don't forget, right in front of this would be plus 2 y sub n minus 1, because that next to the last base has been used twice. So now let's go through a problem and actually figure out an answer using the trapezoidal method. All right, so we've got y equals 2x squared plus 3. We're going to go from x equals 0 to x equals 6 with 6 trapezoids. All right, so what I'm going to do is, first of all, just get my values here. So we'll go 0, 1, 2, 3, 4, 5, and 6. Substitute those into my equation, 2x squared plus 3. I'm going to get 3 when I put in 0. I'm going to get 5. And then I'm going to get 11. For 3, I'm going to get 3 squared is 9 times 2 is 18, plus 3 would be 21. If I put in 4, I get 4 squared is 16 times 2 is 32, plus 3 would be 35. If I put in 5, 5 squared is 25 times 2 would be 50, plus 3 would be 53. And then the last one, if I put in 6, I'm going to have 6 squared is 36, times 2 would be 72, plus 3 would be 75. Okay. So then let's just plot those points. We have 0, 3. We're just going to have to kind of approximate where that's at. We've got 1, 5, 2, 11. And you'll see in just a moment that you actually don't need to graph these. 3, 21. 4, 35. 5, 53. And then 6, 75. And we should see that this should look like a parabola, which it does. And so here's what's going to happen. We're doing 6 trapezoids. I'm going to draw those segments down. And what we do is we just connect the y values at each one of those to form our trapezoids. And then here we go finding our area, and I'll write everything out, but for the most part, you just do this in your calculator. So we're going to have 1/2, and then the height is my delta x. How much are my x's separated out by, which is 1. And then I can read, actually the numbers right off my table from here. My first height or base would be 3. So it would be 3 plus, remember it's 2 times the next base, 2 times 5 plus 2 times 11 plus 2 times 21 plus 2 times 35 plus 2 times 53 plus, and then 75 is only used once. Now at this point you get your calculator and type all that in. Let's see what we get. And I got 164. You might want to double check that. But the area underneath that curve then should be 164 squared, whatever we're measuring in. If that happened to be counted off by inches, it'd be square inches. And that'd be your answer. Now let's look at a couple where the tables are already made up for us, and then just go through how to set those up, and then we'll be finished with this. All right, so here's one where we've got a table. And if you look at your delta x's, the first one is 1 to 3, so that's 2. 3 to 5. Oops. You did a good job drawing that. 3 to 5. Let's try that again. Would be 2. 5 to 7 would be 2. And 7 to 9 would be 2. So I now know that my delta x, or my height, would be 2. So my formula is going to go 1/2, 2. Then it's the first y, 6. 2 times the next one, 10. 2 times the next one, 12. 2 times 16. 2 times 24. And then just add the last one at the end. You don't double it because, again, the first and last sides don't get used twice. Now I'll put that in my calculator. And I got 160. Again, you might want to double check that. But that should be my enclosed area using trapezoidal method. As I said the other day when we're working on Riemann sums, guys, you're probably more likely to see these kinds of problems on the calculator part, or maybe even no calculator part, but in table form. They're probably not going to ask you to draw pictures, but they're definitely going to expect you to be able to take a table and find a trapezoidal approximation. So if you look at the next one, now this one's a little different because this time my heights, or my the height of the trapezoids are not consistent. They're not the same. That's 1. That's 2. That's 1, 2, 4, 3. Okay. Then what's going to happen here is you actually have to do each individual trapezoid and sum them up at the end to get the final answer. Okay, so that would go like this. You're going to have to remember your trapezoidal sum or trapezoidal formula. It's 1/2 height, B1 plus B2. So this is going to go 1/2 for the first trapezoid. The height is going to be 1 from here. And then your bases are your 7 and your 3. The next trapezoid is 1/2 the height, which is going to be 2, and the bases are 3 and 12. Then my next one is 1/2 the height, which would be 1. My bases would be 12 and 5. Then 1/2, the next height is 2. The bases are 5 and 9. Then I've got a 1/2 and a 4. My bases are 9 and 13. 3. My bases are 13 and 16. Then my last one is 7. And my bases are 16 and 22. Okay. And then you grab your calculator, put that in, get a final answer. Let's see if we can do that quickly. So I have 1/2 times 10 plus 15 times 17, 14, 2 times 2, 5 times 3.5 times 38. I came up with 263. Again, check that. But that should be your area using the trapezoidal method. So you should be able to do trapezoidal method in a table, whether the graphs are evenly spaced out for heights or they're not. Because that's the way you're probably going to see this shown on the AP exam.